Hello everyone, and welcome to the second part of the tutorial. We are going to pick up from where we left off in the last class. If you remember, we were talking about spreadsheet modeling as one of the tools that's very commonly used in supply chain management. The first category of applications that we've talked about pertain to demand planning. If you recall, we talked about new venture decisions under various types of conditions, under conditions where you have probability information available to you, and in conditions where that information is not available. So we've talked about various metrics that you could use in a demand planning scenario. We also briefly talked about facility location, and I introduced you to a few heuristics that can be used for facility location, and we also talked about the centroid method for facility location. In today's tutorial, I'm going to expand on that definition. I'm going to expand on the facility location problem that we talked about before, and we're going to talk about optimum facility location, and for that we're going to use Excel's solver tool as the tool of choice. In addition to that, we're also going to talk about transportation and transshipment networks, and together both of these scenarios can be categorized as supply network planning scenarios in supply chain management. So a variety of industrial applications and enterprise information systems help us work with these types of problems. ERP systems in particular would have different modules, different functional modules that have this capability and that have the functionality to work with the types of problems that we are using Excel spreadsheets for. But just to show you what the functionality is and how various algorithms work, how various programs work, that's why we're looking at Excel spreadsheets as the tool of choice. Before I go on to talk about today's problems, I just wanted to touch upon the idea of optimization. That is sort of a prerequisite to our discussion for today. We are, in general, going to talk about a couple of different types of optimization problems. And what I mean by an optimization problem is that it simply refers to a scenario, or it simply refers to a particular hypothetical situation in which you have to select the best possible element from some set of alternatives that you've been provided with. At its simplest, you need to formulate a problem in order to minimize or maximize a certain quantity or a certain function. This could be something like cost of production or the profit that a firm makes. And you do that by systematically choosing between values of variables that you have, and you're given an allowable set of values to choose from, or you're given certain sets of constraints to work within. So with optimization, there are specific terms that are very commonly used. I'm going to introduce you to those terms before we move on to the actual discussion for today. With optimization problems, we talk about the objective function. This is the actual function or quantity which you're trying to maximize or minimize in your solution. So this acts sort of as a scorecard on which you measure how attractive your overall solution is in terms of maximizing your profit or minimizing your cost. The second term here that we're going to use are decision variables. These are the variables that you are trying to change to find the optimum solution overall. So you're trying to come up with optimal values for these decision variables, which will affect your objective function and will change the objective function's value to either increase it or decrease it. So decision variables could be things like the number of units you produce per time period, or it could be the number of units that you're shipping along specific routes if we're talking about a transportation problem. So decision variables are what in Solver you refer to as changing cells. So these are the cells in your spreadsheet that you are going to play around with, and you're going to change the values for these decision variables to see what type of optimum solution or what type of solution you're getting in order to optimize that value. The third term here is that of parameters. Parameters are coefficients or constants in your problem that you cannot change during the implementation or during the formulation of the problem itself. So these are certain things that you've been provided with early on, and you cannot change their value. So this could be something like the cost of production, the unit cost of production, or the cost of distribution along certain routes, and you just have to accept them the way they're provided to you, and you have to formulate them in your problem as such. The fourth term here is constraints, and these are limitations that can restrict the possible choices you have for your decision variables. So you mathematically express these constraints with equalities and inequalities. Greater than or equal to, less than or equal to. There could be upper limits and lower limits to certain things, and you express them as your constraints. So for example, in a transportation problem, there might be a maximum number of units that can be shipped from a particular supply point to different demand points. So that could be a constraint. Or a certain demand point requires a certain number of units to be shipped to it, and that could be a constraint in the problem itself. Once you've taken all of these things into account, you can come up with various types of solutions. And the set of solutions that you can get within the constraints is what is referred to as the feasibility region. So the feasibility region represents all permissible combinations of decision variables, which means that there can be many possible solutions, but using different tools and algorithms, we are interested in finding the best possible solution. And that is why we're using different tools for optimization. Linear programming is one example of a subset of optimization problems. So this is one category of an optimization problem. It's very commonly used in business and economics, along with certain assumptions. And with these assumptions, we can solve various types of problems. One of the main assumptions in linear programming is that your objective function and your constraints are going to be formulated as linear equations, which simply means that you cannot multiply decision variables together. So you can't take products of decision variables, or you cannot use powers of decision variables. So you can't use x squared or x cubed or any of the powers of decision variables. That is the simplest way to think about what linearity assumption is all about. Also, most of the time in your constraints, you're also going to probably have a non-negativity constraint, which again means that your decision variables can only accept positive values or 0 in certain situations. So all of your decision variables, once the solution is formulated, have to be greater than or equal to 0. So that should explain what optimization and linear programming is all about. Again, the term programming should not be confused with computer programming. It has nothing to do with computer programming. You're just formulating a program, or you're formulating a solution to a specific problem. And linear programming is just a technique which is used for resource allocation problems. So you have a complex resource allocation problem, and you want to allocate your resources among various options that you have. And for that, linear programming is a specific technique. There are various ways to solve linear programming problems. We are going to use Excel's solver add-in as a tool for linear programming problems. It solves various types of optimization problems, including linear programming. It's a tool that's available through your Excel spreadsheet. For those of you who are using Excel 2007, you'll have to go into your ribbon. I can show you very quickly where you need to go. So just to quickly show you here, what you can do is go under your ribbon, Excel options, add-ins, and you should see a list of the various add-ins that are enabled, and you should see Solver listed in there. If you don't find this in the list, then you can just click on the Go button here, and it will have a list of add-ins for you to choose, and you could choose Solver from there. For those of you who are using an earlier version of Excel, this item might be under your Tools menu bar at the top, Tools menu item at the top, and you can choose the Solver add-in from there. If you haven't used Solver before, you might want to also look up the tutorial that's available online from www.solver.com/tutorial.htm. This actually is the website for the company that develops various tools, including Excel Solver, and they actually have another premium version of Excel Solver as well for companies that are using this for more advanced types of problems. So you can go to that website to check out more. So Excel Solver, or linear programming in general, is used in supply chain management in various areas for various purposes. These are just a couple of quick examples for where you might see linear programming be used in supply chain management. In our examples today, we're actually using it for a distribution problem or a transportation problem where we're interested in minimizing the total shipping cost or minimizing the cost of transportation between supply points and demand points. That's one category of problems. Another category of problems in supply chain management where linear programming might be helpful are what are known as blending problems. This is where you're interested in allocating or combining different raw materials of different types and grades in order to meet the demand and maximize your profit or minimize your overall cost of production. So blending problems is another example here, especially in organizations where they have access to different raw materials and components and they can mix and combine different grades of those raw materials. Another category would be in scheduling, especially production scheduling. So if you want to allocate your machine time and labor time to various tasks, this is especially relevant in a job shop environment where you want to minimize the total cost of production and minimize your total inventory costs as well. So linear programming provides a good technique to solve those types of problems as well. So there are various applications of linear programming. You can use Solver or another advanced tool for formulating and coming up with the optimum solution for these problems. This company, Frontline Systems, which I've mentioned before, they actually also provide advanced toolkits for developers who want to include this functionality in a program that they're writing or in an application that they're developing for an organization. So we are going to use Excel Solver because that is the most commonly accessible and easily available tool to use for optimization problems, and it will do the job in our scenario. So with that short introduction, let's get started with our transportation problems. That is the category of problems that we're going to talk about today. Transportation problems typically are categorized under network optimization or supply network planning specifically, or these can be referred to as distribution problems as well, because what you're trying to do is come up with the best possible solution to distribute raw materials or components or a finished product from various supply points to demand points, incurring the least possible cost of transportation. First of all, we're going to talk about the notation we're going to use to depict these transportation problems. There are two most commonly used ways of depicting these problems: the transportation grid and a graph diagram. They depict the flows between supply points, which are also known as sources, and demand points, which are also known as sinks. So let's look at a transportation grid first. It's a tabular format representation of demand points and supply points. Along your vertical axis, you have all of your sources or your supply points. In this case, we have 3 supply points, A, B, and C. On the x-axis or on the horizontal axis, you have your sinks or your demand points. In this case, we have 4 demand points, 1, 2, 3, and 4. So the table between these supply points and demand points are meant to show you the actual flow of material from the supply point to the demand point, as well as the cost of transportation between specific supply points and demand points. At the end of the row, what you see is the supply that is possible, the maximum supply that is possible out of a supply point. So in this case, what we're saying is that point A can supply a maximum of 55 units or 55,000 units if we're talking about denominations in the thousands of units. Supply point B can supply 55, supply point C can supply 65. At the bottom of every column, you have the demand for that particular demand point. So in this case, demand point 1 has a demand of 50, demand point 2 has a demand of 40, demand point 3 has a demand of 30, and demand point 4 has a demand of 55. The cells in the table itself are meant to show you the flow as well as the cost of transportation between those points. So that's typically done by showing you the cost in a smaller cell. Underneath that, you will have the flow associated with that supply and demand point. So in this case, what we're saying is it costs $15 per unit of transportation from source A to sink 1, or from supply point A to demand point 1. Similarly, it costs $20 per unit of transportation from supply point B to demand point 2. The flow, once you have determined how many items are going to be supplied, is going to be shown to you underneath the cost cell within that overall cell between the supply point and the demand point. The other notation is a transportation graph or a graph diagram, whatever you want to call it. It uses supply points and demand points as vertices or nodes in the diagram. So you have 3 vertices or 3 nodes for your supply points, and you have 4 vertices or 4 nodes for your demand points. Underneath each of those vertices or nodes, you're given the actual demand or supply that's possible out of those points. If we're talking about a supply point, typically the supply is shown to you in negative. So what we're saying over here is that supply point A can supply 55 units, supply point B can supply 55 units, and supply point C can supply 65. On the other hand, in terms of the demand points, demand point 1 has a requirement or demand for 50 units, and demand point 3, for example, has a demand for 30 units. Along the arcs or along the edges on that diagram, whatever you want to call them, you're also shown the cost of transportation per unit of transportation. So it costs you 15 units to transport materials or products from supply point A to demand point 1. Similarly, it costs $20 per unit of transportation from supply point B to demand point 2, so on and so forth. So that's the second notation that is very commonly used in transportation problems. All right, so now that we know how these problems are depicted in a transportation grid or a transportation graph, we can start talking about how you solve for these problems. We are going to use this as an example for the next little while, and we're going to use various approaches to solve this problem. So we have a transportation grid in front of us. We have 3 supply points, A, B, and C. We also have 4 demand points, in this case D, E, F, and G. We're given the cost of transportation from these supply points to these demand points. That's what's being shown in the smaller cells to you. What we need to do in this case is determine how many units we're going to transport between specific supply points and demand points. In terms of the constraints for this problem, you're given the maximum supply that is possible out of each and every supply point. So supply point A has a maximum supply possible of 50 units or 50,000 units, whatever the denomination is. Supply point B has a total capacity or has the ability to supply 40 units, and supply point C has the capacity to supply 75 units. Similarly, at the bottom of every column, you're also given the demand or the requirements for those demand points. So 50, 60, 25, and 30 units are required at demand points D, E, F, and G. In this particular problem, if you notice, our total demand is equal to total supply. And this is an example of a balanced transportation problem where the demand is equal to the supply. So we don't have to worry about an instance where one of our demand points might fall short of what its requirements are. So in a problem like this, it's pretty simple to solve because we do not have a situation where either the supply is shorter or lesser than the demand, or there might be specific supply points that might have excess supply. Before we actually try to find the optimum solution for this problem, though, I am going to show you 2 heuristic approaches or manual procedures which you could use to find a feasible solution to this problem. It's not the optimum solution, a feasible solution though. So that's a starting point in case you did not have access to Excel Solver, for example, or any other tools to find an optimum solution. There are other manual procedures that you can use, and some of these are very, very simple to use. 2 which I am going to demonstrate to you are the northwest corner rule and the intuitive lowest cost method, which is also sometimes referred to as the greedy heuristic, because you're trying to be greedy and save as much as possible. So let's look at those two heuristic approaches first. In the northwest corner rule, as the name suggests, what we want to do, or the procedure that we need to follow, is that we start at the northwest corner, or the top left side of our table, and try to fill in cells from left to right, top to bottom. So that is the objective, or that is the procedure that you're going to follow to try to find a solution for this problem. So it's a very simple rule to follow. It will take a little bit of practice the first couple of times you work with this, so I will post the animation for what I'm doing right now online as well, so that you can go through it step by step and see what actually is happening. So let's do this, and we are going to start with the top left-hand cell, which is from A to D. So the way you're going to read this information is that D, for example, requires 50 units. A can supply 50 units, so that's fine. So what we can do is we can satisfy all of the demand for D from A. So we're going to supply 50 units. That actually is going to exhaust the supply out of A, and it's also going to satisfy all of the requirement for D. So I'm just going to cross those demand and supply numbers off so that we know that we've taken care of it already. Moving on, the next cell is A to E, but again, A has exhausted all its supply, so we can actually skip over the row because we know that A cannot supply any more units to E, F, or G in this case. Moving on to the second row, the first cell is from B to D. However, D does not require any more units. All of its requirements have been satisfied from A in our previous step. So this cell we do not have to worry about. B to D we do not have to worry about. Move on to the next cell, which is from B to E. Again, read the information that's available to you. E requires 60 units. B can supply 40 units. So even though we're not going to be able to satisfy all of the demand for E, B can certainly supply 40 out of the 60 units that are required. So let's do that. So now we've supplied 40 units out of B, which exhausts the supply from B. However, we have not satisfied all of the requirements for E just yet, so we cannot really cross off the demand number for E. But keep in mind that we've already supplied 40 out of the 60 that are required, so E needs 20 more. Moving on to the next cell, that's from B to F. However, B has exhausted all its supply. Similarly, from B to G, we can't do anything because B has exhausted its supply. Next row is from C to D. D does not require any more units. We've already satisfied the demand for that point, so move on. From C to E, C can supply 75. We haven't touched the supply for C yet. E still requires 20 more units. It required 60, but we've already supplied 40, so it needs 20, which can be supplied by C. So let's do that. And that will take care of the demand requirements for E. So now we've satisfied the requirement for E at this point. Move on to the next cell, which is from C to F. We haven't touched F yet. F requires 25 units. C had the capacity for 75, out of which we've already used 20. So we still have 55 units that we can supply. So we will supply the 25 that are required at F, which will take care of all the requirements for F. Now we're left with 30 units that C can supply because C had original capacity of 75, and we've supplied 25 and 20. So 30 still remain. And luckily in our case, G requires 30 and C has those 30 units. So we can supply those 30 units, take care of the demand for G, and you've also now exhausted the supply from supply point C. So that basically completes our solution. We've actually satisfied all of the demand for the various points, and we've exhausted all our supply. This was, again, a case where supply was equal to demand, so this was a balanced problem, so you would have had to exhaust all of your supply from various points in order to meet the requirements at the various demand points. So that's your solution then. What we are seeing then is that A is going to supply 50 units to D, B is going to supply 40 units to E, C is going to supply 20 units to E, 25 to F, and 30 to G. Also, the cost of transportation per unit is given to you, so it's going to cost you 50 times $9 for the transportation between A and D. It's going to cost you 40 times 8 for the transportation between B and E, and same thing for C to E, C to F, and C to G. So your overall cost of the solution then is simply the sum product of flows and costs. We've talked about sum product in the previous class, which is just a way in Excel to multiply two different arrays of numbers together. So in this case, what we are trying to do is multiply 50 times 9 plus 40 times 8 plus 20 times 3 plus 25 times 3 plus 30 times 10. So in Excel, you could do that very easily if you had two different rows or columns, one with your flows and one with your costs. You can multiply those together and take the product using sum product. So your overall cost of transportation in this case is $12.05. So that is our cost of transportation using the northwest corner rule, which is one of the heuristics or one of the manual procedures or simple ways that you could use to come up with a feasible solution to the problem. Not the optimum again, just a feasible solution to the problem itself. So this should give you a little bit of an idea of a heuristic approach to a transportation problem. It's a simple procedure that can be used to come up with a feasible solution. Another example of this problem that we're going to see, or another example of a procedure that I'm going to show you, is the intuitive lowest cost method, or the greedy heuristic. And in this procedure, we are interested in explicitly taking into account the cost of transportation from various supply points to various demand points, and choosing the option that costs us the least. And we're hoping that by doing that, the overall cost of transportation is going to be lesser than what we've seen in our previous approach. The procedure to follow for this heuristic is that from the various options that are available to you in your transportation grid, you are going to choose a cell that has the lowest cost among all of the other cells, and you're going to try and put the maximum flow of materials or products in that cell. So in this grid, for example, we have various cells with different costs. So for transportation from C to E, for example, it costs you $3, while transporting from C to D costs you $5. So what you're going to try to do is, if you had the option between those two scenarios, you would try and maximize the transportation from C to E as opposed to from C to D. So you start with the lowest possible cost that you have in the grid at that point in time. So let's get started then. In this example, we actually have a cell which has a cost of 0 associated with it, and that is from B to G. So you have a supply point B and a demand point G, and the cost of transportation between those 2 points is actually $0. If you're wondering why or how that is possible, this might be a scenario where you have a warehouse location, and that warehouse location also acts as a retail outlet. So if that is the type of scenario we're talking about, then yes, our cost of transportation is going to be very low, or $0 as compared to the other costs of transportation. So we are going to try to fill out that cell first, or allocate the maximum number of units to that cell before we move on to the next cell with the next lowest cost. So let's try to do that then. B in this case can supply 40 units. G, however, requires only 30 units. So we're going to try and maximize the flow from B to G, and we could supply 30 units. That will take care of the demand for G, so we could cross that out. B still, however, has 10 more units left that it can supply to any of the other points, so we cannot cross out the 40 units for B just yet. B still has 10 more units that can be allocated elsewhere. Moving on from the $0 cost to the next best cost that you see in this grid, we have a couple of cells here which have a cost of $3 associated with it. The cell C to E, or the cost of transportation per unit between C to E is $3, and the cost of transportation between C to F is also $3. If you have a situation like this where there's a tie between two options that you have, it's really up to you how you want to break the tie. You could arbitrarily break the tie using any procedure you want. Some procedures, of course, are better than others for breaking the tie. In my example that I'm showing to you, I'm actually just going to break the tie by taking the cell that is on the left or taking the cell that's above the other cell. So in this case, I have a tie between CE and CF, and I will arbitrarily just try to satisfy the flow from C to E before I do the flow from C to F. So in this case, C to E, if you look at that cell, then E has a requirement of 60. C can supply to a maximum of 75, so we will be able to satisfy all of the demand for E and supply 60 units from C directly. That will take care of the demand for E, so we could cross that out. The next cell that we have here is the $3 cell again, from C to F. F requires 25 units. C, you've already supplied 60, so C only has 15 more units that can be allocated elsewhere. So we will try and supply the 15 from C to F, which will take care of, or which will exhaust the supply for supply point C. So C cannot supply any more units now. We've only satisfied the demand up to this point for E and G, and only 15 units for demand point F. F still requires 10 more units from somewhere else. Next up, after $3, there's a couple of cells which have a cost of $5 associated with it. And like I said, based on the tie-breaking rule that I'm using, I'm going to choose the cell that comes first from top to bottom, left to right. So I would like to use the cell from A to G. However, G does not require any more units. I've already satisfied the demand for G, so I don't need to do anything in that cell. The next cell with $5 cost is from C to D. D requires 50 units. C, however, cannot supply any more units. It's already exhausted its supply, so I can't do anything in that cell either. From $5, the next one up is the $6 cell over here from A to F. A can supply 50. F still requires 10 more units. So let's supply those 10 units from A to F. After supplying the 10 units from A to F, you've now satisfied the requirements for F. So you could cross that out. And now you can move on to the next cell after $6. So you have 3 cells now which have a cost of $8 associated with it. So you don't need to do anything in for these 2 cells from A to E or B to E, because E's requirements have already been satisfied. Similarly, you don't need to do anything from B to F because F's demand has already been satisfied as well. Move on from the $8 cost to the $9 cost that you have. From A to D, there's a $9 cost. From B to D, there's a $9 cost as well. So we're going to supply from A to D first. D requires 50 units. A, however, has already supplied 10 out of its total possible of 50, so it can now supply 40 to D. So we will do that, which will take care of the total supply that was possible out of A. So A is now exhausted all of its capacity. Next cell below is from B to D. B can supply 40. D still requires 10 because you've supplied 40 out of the 50. So let's supply those 10 out of B, which will now take care of the demand for demand point D as well. B in this case has also now supplied the total that was possible, 30 plus 10, and that was the total that was possible out of B to begin with. So we've now exhausted the total supply out of B as well. So now, again, we've crossed out all of our supply points and demand points. We've met the demand requirements and we've exhausted all our supply. And this is the solution that you get using the intuitive lowest cost method. Again, to find the total cost in this solution, we're going to multiply the flow times the cost. So 40 times 9 plus 10 times 6 plus 10 times 9 plus 30 times 0 plus 60 times 3 plus 15 times 3. Or in Excel, you could just do a sum product of the flows and costs, and that will give you $735, which is much less than what you saw in the previous scenario where our total cost was $1,205. So this does give you a better solution than the previous procedure. However, both of these solutions are feasible. They're not optimal. We don't know whether these are optimal or not, but they are feasible solutions. So that is the intuitive lowest cost method, and it does give you another option to choose for your decision variables. So the decision variables that we've changed in this case are the flows from the various supply points to the demand points. And by changing the values for these decision variables, we've come to two different solutions, and both of these are feasible solutions. So now that we've seen two different heuristic procedures to solve a transportation problem, we're ready to talk about the optimum solution. And for that, we're going to use linear programming to solve the transportation problem. Again, I've already defined linear programming for you, where we have different parts of the problem. So the objective function in the transportation problem is to minimize the cost that's associated with transportation, which is the sum of flow times cost between the various demand points and supply points. In terms of the constraints of a normal transportation problem, your supply from the various sources should not be exceeded from the maximum capacity of those supply points, which we just saw in the previous case. The demand at the various demand points or sinks should be met as well. That's your other constraint. The flows and costs should both be non-negative. The costs are typically given to you in a transportation problem, so those are considered to be the parameters of the problem. Flows are your decision variables, and that is what you're trying to work with and get different values for to find the optimum solution to the problem itself. These constraints, however, might need to be adjusted if our supply exceeds our demand or our demand exceeds our supply. So the greater than or equal to sign or the less than or equal to sign or the equality sign will need to be changed depending on the actual scenario itself. And I will show you a couple of more advanced examples in a bit for these unbalanced transportation problems where the supply and demand might be different. Also, in certain problems, there might be infeasible routes, so where you do not really have a route between a particular supply point and a demand point. In those situations, what you typically do is assign an arbitrarily large number as a transportation cost between those points. So if we are talking about costs in hundreds of dollars, you can assign a cost in tens of thousands of dollars between a supply point and a demand point, and that will take care of that route, and solver or any other optimization tool you're using will probably not use that route at all. In terms of formulating this problem, I will show you the formulation or express the formulation manually before we actually formulate this in Excel. The formulation, what we're trying to do is minimize the total shipment cost or minimize the total transportation costs from the origins to the destinations. The origins have a supply that's possible out of those points, and we denote that as S sub I. The destinations or the demand points each have a demand which we denote as D sub J. So I and J again are just indices that we're using for various supply points and demand points. The unit shipment cost from point I to point J is C sub ij. So C sub ij just simply shows you the cost of transportation from one supply point to another demand point. So this is what the mathematical expressions look like for your objective function. So your objective function here is to minimize the cost of transportation between supply and demand points. Cost is given as C. And the flow is given as X. So what we're saying here is for all I and J, multiply the flow times the cost from I to J. and take the sum of that over the entire transportation grid or the transportation graph. That's what you're trying to minimize. Again, it might look more complicated than it really is, but if you've understood what we were doing in our heuristic examples, this is exactly how we calculated our total cost of transportation. In terms of the constraints, again, if you look at the constraints that are given to you using various types of inequalities, what we're saying here is for each supply point or for each origin I, everything that's coming out of I should be lesser than or equal to the total possible supply for that supply point or for that origin. So in this case, what we're saying is for all j, starting from j equals 1 to j equals n, which are all of your demand points, everything that's coming out of I and going to these various demand points, the sum of that is lesser than or equal to the total supply out of that supply point. For each destination, which is your second constraint for your demand points, each of those destinations has a particular demand or requirement, which we denote as d sub j. So everything that's going into j, so from all of the i's into that particular demand point j, take the sum of all the flows into that demand point, and that should be equal to the demand for that demand point. Also, all of your flows, which are shown as x, are greater than or equal to 0 for all I and j. So for all of your supply and demand points, any flows in your solution should be greater than or equal to 0. So that is the non-negativity constraint that I spoke of before. So that is your formulation for a general transportation problem. Like I said, the inequalities might change a little bit, or there might be additional constraints depending on if we're talking about a more complex problem. So let's go back to our example, which I've shown you before. So this was the transportation grid that was given to you for that example. Again, 3 supply points A, B, and C, 4 demand points D, E, F, and G. You're given the constraints for the supply for each of the supply points. So A can supply to a maximum of 50, B can supply maximum of 40, C can supply maximum of 75, and you're given the constraints for the demand points. So requirements for D are 50, requirements at E are 60, at F are 25, and at G are 30. This again is an example of a balanced problem, so it's very easy to solve. I'll show you the manual formulation before I move on to the Excel spreadsheet formulation of this. In the formulation, I'm going to again use x sub ij as the flow from node I to node j. So x sub ad will show the flow from A to D. So let's look at what our objective function will look like. So this is our objective function. So the flow from A to D is x sub ad. Multiply that by the cost of transportation from A to D, which is $9. Add that with the flow times the cost from A to E. Add that with the flow times the cost from A to F. And do that for all the cells. So in this case, you have 12 total cells, and you have 12 combinations of costs and flows. So you're trying to minimize this sum. That is what you're trying to do. So the flow times the cost for every single cell that's given to you in that transportation grid. That is your objective function, to minimize this total cost. In terms of the constraints, if you look at the constraints, then what we're doing in the first set of constraints here, which are your supply constraints, is we're saying that everything that's coming out of A, so x sub AD, plus x sub AE, plus x sub AF, plus x sub AD, so that's everything that's coming out of A, or going from A to D, A to E, A to F, and A to G. Sum of that should be lesser than or equal to 50, which is the maximum possible supply. Similarly, everything that's coming out of B and going to D, E, F, and G has to be lesser than or equal to 40. Everything that's coming out of C and going to D, E, F, or G has to be lesser than or equal to 75. So those are your supply constraints. Similarly, for your demand constraints, we work by columns. So everything that's coming into D, so either it's coming from A or B or C, so take the sum of that, and that has to be equal to 50. Everything that's coming into E from A, B, or C has to be equal to 60. Same thing for F, same thing for G. The inflows into F and G have to be equal to 25 or 30. The last set of constraints, like I said, are your non-negativity constraints. So all of your flows are positive. So x sub ij is greater than or equal to 0, where I is either A or B or C, and J is either D, E, or F or G. So those are your supply points, those are your demand points, and what you're saying is all of the flows between the supply and demand points are greater than or equal to 0. So you cannot have a negative flow in the final solution that you work on from your tool. All right, so with that, we're ready to go into Excel and solve this problem using Excel's solver add-in. Before I show you how to formulate the problem itself, this is what the solution will come out to be. The overall cost I've already calculated using the solver add-in tool is going to be $720, which again is lesser than the two procedures that we just used for the various heuristics. So with the northwest corner rule or the intuitive lowest cost method, both of them gave us feasible solutions, but they were higher than $720. So $720 after using Excel solver, you'll know, is the optimum solution or the lowest possible transportation cost that you're going to have. So with that, let's go into Excel and show you how to formulate this problem. So this is the data that I've been given already. And again, this is exactly the transportation grid that I showed you in the slides. So you have 3 supply points or sources, you have 4 demand points or sinks, you're given the cost of transportation between the supply and demand points, and you're given the maximum that can be supplied out of A, B, or C. You're also given the demand requirements for D, E, F, or G. And that's the data that you have. So the first thing I'm going to do, and this is the simplest way of working with transportation problems, is to replicate that information table that you have from your data into the actual model that you're trying to solve. So I'm just going to copy over this table. And this time around, however, I'm not going to have the cost in the cells. I actually want to fill these cells with the flow from A to D, A to E, A to F, A to G, and so on. I'm also going to change the format of these cells because in my data, these cells are a currency. I'm just going to right-click and change them into general cells. And I'll also shade them a little differently. And these are the cells that I want Solver to fill in for me. So Solver will tell me what the values for these cells are. I don't have to fill them out. Also, instead of having the maximum supply and the demand requirements from the various supply points and to the various demand points, I'm going to delete those values. And instead what I'm going to have are the total outflows and the total inflows. So what is coming out of the various supply points and what is going into the various demand points. So these are now going to be my outflows. And your outflow is simply the sum of everything that's coming out of A. So once Solver fills these cells for me, I just simply want to add them up. So I'll take the sum of this row, which will give me the outflows from A, and I do the exact same thing for the other 2 cells as well. So for supply point B, I want to take the sum of everything that's coming out of B. And for supply point C, I want to take the sum of everything that's coming out of C. Similarly, at the bottom of every column, I want to have the inflows into D, E, F, and G, which simply means I'm going to take the sum of everything that's going into D. Similarly, everything that's going into E, F, or G. So everything that is being provided from the various supply points to that specific demand point. So you're taking the sum of column and representing that as your inflow. The reason we're doing this is because in our constraints, we want to make sure that our outflows are lesser than or equal to the maximum that can be supplied. and our inflows are equal to the demand requirements for those demand points. So this now becomes your model, or what you're trying to solve for. So let's just depict that. And we're basically ready to use solver. But before we do so, we also need to have an objective function. And if you remember, the objective function simply is the sum product of your flows and your cost. So my total cost then is going to be simply the sum product of your cost grid and your flow grid. And again, remember that flow grid for now is empty. We want solver to solve this for us, so this will get filled out eventually. So that is your total cost. And again, let me just change the format for this, and I'll make this into a currency cell. And that should take care of my objective function. So I have my objective function, which is your total cost. You have your decision variables, which are your flows from various supply points to demand points. You have parameters, which are your costs of transportation. You also have your constraints, which are your outflows being lesser than or equal to the maximum supply, and your inflows being equal to the demand requirements. So with that, we're ready to go into solver and specify our constraints in our objective function. In Excel 2007, you will find the solver tool under data. So go into solver. The first thing which you have to fill in is your target cell, which is your objective function that you're trying to maximize or minimize. So just select your total cost here. And what we're trying to do with this cell is we're trying to minimize it. So click on minimum or minimize. The changing cells is where you will define your decision variables or the variables that you're changing. In this case, it's the flows from various supply points to demand points. So just select that matrix or array of cells that you want to change. And then you add a couple of constraints. So the first set of constraints that we're going to add are that the outflows that you have from points A, B, and C have to be lesser than or equal to the supply that's possible out of A, B, and C. So you add that. And the second constraint that you have are that your inflows into D, E, F, and G are equal to, so you have to change that sign to equal to, the requirements for D, E, F, and G, which is given to you in your data matrix. So that is your second constraint for your problem. So you click on OK, you have two sets of constraints, you have your changing cells, you have an objective function that you're trying to minimize. That is the basic information that you need to provide to solver. Also, you need to go under options and make sure you check mark the assume linear model and assume non-negative, because this is an example of an LP or linear programming solution that we're trying to come up with, and all of our flows should be non-negative. The other options that are available to here, don't worry about them. It's beyond the scope of our tutorial for me to explain what these options mean. You can just let the default be and click on OK, and then click on Solve to see what solution you're given. So click on Solve. It solves the problem for you. You see your total cost is $720. You can either keep the solver solution or we can restore your original values. You could also look at various types of reports. The sensitivity report in particular is very useful. It actually gives you information on if you were to change your parameters around a little bit, what would the effect be on your total cost or your objective function. Again, we're not going to choose those reports, but if you wanted to, you could always choose the report if you wanted to. So I'm just going to click on OK, and this will now save this solution for me. So I have the solution now in my spreadsheet, and I could save the spreadsheet, and next time I open it up, it'll have the solver options already filled out for me according to what I've just done. So that's how solver works. It's actually filled out all of our cells for us. And what's being shown to you here is that you're going to supply 25 units from A to D, 25 from A to F, 10 from B to D, 30 from B to G, 15 and 60 from C to D and C to E. Overall, that would allow you to satisfy all the requirements for the demand points. Your total outflows, if you look, are equal to the maximum that could be supplied out. Again, this was a problem where you had balanced supply and demand, so you've exhausted all of your supply while satisfying the requirements at the various demand points. So I'm hoping this gives you an idea as to what Solver can do and how you go about solving linear programming problems in general. So that is a very simple example of a transportation problem. This was again extremely simple because our supply and demand were balanced. We did not have to deal with infeasible routes. But if that were part of your problem, then you would need to do something a little different. And that's what I'm going to talk about next, some of the variations that you could have in these transportation problems. Some of these variations are things such as your supply not being equal to demand, or you might have a maximization objective function. Maybe the objective function in a specific scenario might not be about your transportation cost. It might be about the profit that you're making or the revenue that's being generated. And in that case, it might be a maximization objective function. Sometimes the capacities on various routes might have a maximum or a minimum, so you have to take that into account as well. And like I said, infeasible, unacceptable, or prohibited routes might be another part of the problem as well. So you have to take that variation into account as well. So those are some variations. I'm again going to just talk about a couple of these variations. And there's an assignment question where you'll have to work with one of these variations as well. The first variation, and a very common one at that, is that your demand might be greater than your supply. So whatever the capacity is for your various supply points, the demand points have more requirements than that. There are a couple of ways to resolve this. The simplest way of resolving this is by adding what's called a dummy node for your supply points, or a dummy origin node. And the dummy origin node can supply the difference between the demand and supply to one of the particular demand points. So any demand point that receives some supply from this dummy node will be the one which will eventually fall short of its total requirements. So that's the concept behind the dummy origin. The way you incorporate this into your solution is that you assign a zero cost of transportation from this dummy node to every destination node. So what you're doing is you're not really affecting the overall minimum cost, because now you're including cost of zero. But this problem now becomes solvable, because now what we're saying is that any difference that exists between the total supply and total demand can be provided by this dummy node, which does not exist, but for purposes of solving this problem using a balanced notation, we could do something like this. Also, another variation which we're going to use, I'll show you an example of this, and you're going to use this in your assignment as well, is a transportation problem in which some shipments actually go to an intermediate node before reaching the destination node. And these are referred to as transshipment problems. So you might have a warehouse or a distribution center or a cross-docking station of some sort which accepts the supply from various supply points, and then it transfers them to the final demand points. So those are transshipment problems. You can again use a similar procedure to solve these problems as I've shown you before. And they can be formulated using linear programming as well. The main difference here, or one of the key things that you need to take into account here, is that the intermediate nodes, or your transshipment points as they're referred to, usually net out to zero. So everything that's coming in will eventually be equal to everything that's going out of these transshipment points. So the inflows are equal to the outflows in these problems. So this is an example of a transshipment problem depicted as a transportation graph. So I have two supply points here, 1 and 2. I have 3 transshipment points, 3, 4, and 5, and I have 2 demand points, 6 and 7. You are given the cost of transportation between these various supply, transshipment, and demand points, and you can solve this problem very similarly to a linear programming problem using just supply and demand points. The way you do this is by breaking the problem into 2 parts. Break the problem at the transshipment point and first look at the part where we're considering the supply points and the transshipment points, and then look at the part of the problem from the transshipment points to the demand points. So if you break the problem into 2 parts, it becomes a little more manageable to solve. If you were wondering how you would formulate this, again, the formulation, the expression is very similar to what I've shown you before. If you look at the objective function, however, we have broken down our objective function into 2 parts as well. So the first part is from your supply points to your transshipment points, and the second part is the cost of transportation from your transshipment points to your demand points. And you take the sum of those 2 values, and that is what you're trying to minimize. Also, your supply points will have a maximum. So for each origin, basically what you're saying is everything that is going into a particular transshipment point, everything that's going out of the transshipment point, that needs to be taken into account as well. And if you look at each transshipment point, the inflows minus the outflows should be equal to 0. So everything that's going into the transshipment point minus everything that's going out of the transshipment point should be equal to 0. So when you formulate the problem, you will have to have this one additional constraint in the problem itself. Otherwise, the other constraints are very similar to what we've seen before. So this is the example that I'm going to show you. We have 3 supply points in this case at Flint, Fresno, and Monterey. And you have 2 transshipment points at Santa Fe and Jefferson City. For your demand points, you have 2 demand points at Phoenix, Davenport, 3 demand points at Phoenix, Davenport, and Columbia. So those are the supply, demand, and transshipment points that you've been given. Again, if you look at how this grid is organized, it's split into 2 parts. The first part is from your supply points to your transshipment points, and the second part is from your transshipment points to your demand points. So this is what we're going to work with. I will show you this example in Excel, and I will post the solution online as well so you could follow it in your own time. Before we do that, I just wanted to bring up this second example as well. In this case, again, you have supply and demand points and transshipment points. You're given the cost of transportation per unit or per thousands of units, whatever the denomination might be. In this particular example, however, there are a few things to notice. First of all, you do have transshipment points. You do have these intermediate nodes that need to be taken into account. Also, these transshipment points have their own demand, which is possible. You may or may not see that situation occurring. Like I said in a previous scenario, you might have a warehouse where you're also catering to the needs of various customers. So these transshipment points might have their own demand. So Sacramento, for example, has a demand of 25. Chicago, for example, has a demand of 47. Sunnyvale, Dublin, and Bangkok are your 3 supply points, and they just have outflows possible for 45, 120, and 95. So in this scenario, you do have transshipment points with their own demands, and you have demand points with their own demands as well. So that's one thing which is different about this problem. Also, if you add up the total supply and the total demand, in this example, the total demand is more than the supply. So this is an unbalanced problem. So we will have a dummy node which we will use to supply to the various transshipment points and your demand points. So this is another transshipment example which is a little more advanced. However, for purposes of an example for the tutorial, I'll go back to the previous slide, and this is the example that I'll show you how to work through this using Excel. Okay, so let's go into Excel and try this problem. I've already formulated my basic data that I have from that problem. So I have two grids in this case. The first, or two parts to my overall transportation problem. The first part shows me the information from plants to various warehouses, and the other part shows me the information from warehouses to the retail stores. So I have the cost of transportation from plants to warehouses, cost of transportation from warehouses to retail stores. In terms of my constraints, I've been given the constraints for the plants in terms of their production, and I've been given the constraints for the demand at various retail stores. So that's the data I've already been provided with. As I've done in the previous example, I'm going to just copy the data into the model itself, and we'll formulate the model from that. So for the model itself, if you remember, we're going to use the exact same grids that we have in our problem, except instead of cost, we're going to have flows. So let me just change that in both of my parts. So you're going to have flows, and Excel is going to fill out this information for you. So let's shade them a little differently as well. We'll change them into red so that we know that these are cells which Excel will change for us. Also, rather than having the capacity and the demand requirements, we will have the outflows from the various plants and the inflows into the various demand points or our retail stores. Again, we will just get rid of the numbers that are already in those cells to have the outflows and inflows. We will have to formulate these outflows and inflows. So your outflows are just going to be the sum of that row, or the flows in that row. So what we're saying here is that we want to take the sum of everything that's coming out of Flint, the sum of everything that's coming out of Fresno and Monterey, and what you're doing for your demand points or your retail stores is you're taking the sum of everything that's going into Phoenix and sum of everything that's going into Davenport and Columbia as well. So once Excel fills these cells for us, we will have the outflows for the plants and the inflows for the retail stores. However, in addition to just having outflows and inflows for your plants and retail stores, which are your supply points and demand points, we also have transshipment points in this case. So we need to have inflows and outflows from that transshipment point. So a transshipment point will have both inflows as well as outflows, and we want to make sure that we set a constraint where the inflows are going to be equal to the outflows. So let's do that as well. So go to the first grid and also have your inflows to the warehouses. And this will just simply be the sum of this column, which shows you everything that's going into Santa Fe. And similarly, everything that's going into Jefferson City. So you need to have the sum of that column for that warehouse. So these are your inflows into the warehouse. And you want to have the outflows from the warehouse as well. So we should have that. And you'll have the outflow from these various warehouses. So that is going to be in your second part of the grid. And that will simply be the sum of everything that's going out of those two warehouses as your outflow. So we need to do that for Santa Fe and Jefferson City, both of those. So now that you've specified your problem, so we can simply go into Solver now. But before we do that, we will have to also specify our objective function, which we haven't done yet. So let's do that. So our objective function in this case is going to be a combination of two things. It's going to be a combination of the flows and cost between the plants and the warehouse, and secondly, the flows and cost between the warehouses and the retail stores. So let's formulate that in two parts. So the first part is going to be cost of transportation from plants to warehouses. And the second part is going to be the cost of transportation from warehouses to retail stores. And again, just as we've done in the past, we will just take the sum product of the flows and cost. So in this case, it's going to be the sum product of my flows between plants and warehouses and the cost between plants and warehouses. And the second component of my cost equation is going to be the sum product of my flows between warehouses and retail stores and the cost between warehouses and retail stores. So those are your two components to the cost, and your total cost then is simply going to be the sum of these two components to your cost. So let's format these cells to be currency cells, and we want Solver to minimize our total cost for us. So let's just format that. And now we're ready to solve this using the Solver tool. So let's go into Solver. Again, go in the data menu under Solver. Let me just reset everything here. So what I want to do is set the target cell to be equal to the total cost. I want to minimize this. Also, I want to have two sets of changing cells in this case. So there are two sets of cells which are shaded in red here, which I want to change. So I will choose the first set, and I'll hold the control key and also select the second array of cells that I want to change. So Excel Solver will take into consideration that these are two sets of cells that I'm changing. For my constraints, first I will put in my normal constraints where the outflows from my plants have to be lesser than or equal to the production. They have to be lesser than, the outflow from the plants has to be lesser than or equal to the production capacity of those plants. That is your normal constraint. The second normal constraint that we've had before is that your inflow into the retail stores has to be equal to the demand requirements for those retail stores. That still holds. The last constraint, which is new in this case because of the transshipment problem, is that the inflows into your warehouses, which are these two cells here, have to be equal to the outflows from your warehouses, which is these two cells over here. So you have to add that additional constraint in this case. So we have three sets of constraints now. Go under options and again make sure that assume linear and assume non-negative are checked, and you can now solve the problem. So what we have in our solution then is that it's going to cost us $12.85. We will be able to satisfy the demand at the retail stores. It was 35, 30, and 35. And we've exhausted all of our supply from the various plants. 43, 26, and 31 are the capacities that were given to us, and the outflows from those plants are equal to those exact numbers. So we've been able to solve this problem using one additional constraint where the inflows into the warehouses are equal to the outflows from the warehouses. The other two sets of constraints where your demand has to be satisfied and your supply from the various plants has to be lesser than the capacity, that still holds. So this completes our solution to this transshipment problem. Again, I will post this spreadsheet online with ample instructions so that when you're following this in your own time, you can look at the solution and make sense of it.